All right, we're just gonna wait a couple more minutes. Can you hear me all right?
Yep, you're good.
Yes, yes.
All right, cool, thanks. I'm just gonna start in one more minute. All right, hey, Saketh, can you hear me?
Yes, one, I can hear you.
Okay, great. So then we'll just proceed as planned in the presentation as we discussed.
Sounds great. Sounds great.
All right, thanks. All right, just muting the last few people into the room. All right. Yeah, sorry. Waiting 30 more seconds because currently I'm trying to admit people in the room and also I'm going to start the meeting. So once I start, it's going to be hard for me to admit people. Or let me, is there anyone here who can help me just admit people? I can
I can do that
designate
if you
you.
want.
Yeah, Besher. Okay, I'll designate you a co-host. All right, cool. So then, yeah, Besher, can you just admit people as they're coming in?
Sure,
Then I can
sure.
start. All right, thanks a lot. Okay, so y'all can hear me okay?
Yep.
Yes.
Yeah, cool. All right, let's just start. So chapter 7, here we are, model deployment. This chapter is about deploying models in production environments, different prediction paradigms, online versus batch, model compression, and trade-offs between ML and the cloud and the edge. Glad you've all stuck around to this point. So we have 4 more chapters after this. Keep it up. Okay, so unfortunately, the team that was assigned to this chapter didn't make it, save for one person. That survivor, Saketh, and me, Vern, will be presenting as backup team or B team. You already know me as the book up TA and the first week presenter, so I'll skip my bio. But here's my fellow B teamer, Saketh, to make an introduction. Saketh?
Yes. Hi, everyone. Very happy to present today. I'm Saket. I'm currently a master's in electrical engineering student from UC Riverside. And I hope to give some of my insights gained throughout past couple of years and hopefully have time for some good discussion. Back to one.
All right, thanks, Saketh. So because we lack the manpower, I resorted to a Gen AI presentation application called Gamma to help generate these slides. So about 75% of this content presented here is AI generated, most of the layouts, images, and quite a bit of the descriptive text. So some of the slides were overly verbose, and I tweaked some of the responses and manually added a few slides. But speaking as a former product manager that did customer-facing presentations, I can kind of get why Elon says AI will take all our jobs. So this chapter starts with 4 ML deployment myths. The first myth, you only deploy a few models in production. In reality, there could be hundreds or even thousands of models. Here's an oversimplified hypothetical example with Uber. Say it is operating in 20 countries, each with 10 models to account for different regions, user profiles, etc. That's already 200 models right there. According to the book, Uber actually has thousands of models in production. Second myth, if you don't do anything, the model performance remains the same. We all know that the performance of any software system degrades over time. So with ML systems, data distribution shift of training to production is an additional factor to account for. The third myth. This is closely related to the second myth. You don't need to update the models frequently. So actually, you do, because the ML system performance will degrade otherwise. For example, Weibo and TikTok updates their models once every 10 minutes or so. The fourth myth, ML engineers don't need to worry about scale. It seems like only a few big tech companies with massive user bases only need to worry about that. However, as a collective, they employ a majority of the MLE workforce. And if you're working in ML, you need to understand how to scale your application in terms of data and users, since big data is one of the big enablers for this recent ML renaissance. So batch prediction versus online prediction. How does your ML system generate and serve predictions to users? So the book is quite pedantic about there being three modes of prediction. The first is batch prediction is when predictions are generated periodically or when triggered. This mode uses only batch features, which is features that are collected periodically, stored in databases or data warehouses. Number two, one form of online prediction is when predictions are generated and returned in real time, but it uses batch features. The other form of online prediction is one that uses both batch and streaming features, and particularly in the special case, if it uses streaming features from real-time transports, this is also known as a streaming prediction. There are use cases where batch and online predictions are used in the same ML system, which requires unifying or integrating the two pipelines in some way. So what are the pros and cons of batch prediction? Batch predictions are good when generating a lot of predictions, but don't need to serve all the results immediately. This can leverage distributed computing for high volume processing of samples, which in turn can be used as a trick to reduce the perceived inference latency since you're just retrieving pre-computed results. The problem with batch prediction is that it makes the model less responsive to the user's changing preferences. For example, a Netflix user could be sick of binging one genre and immediately wants to switch to another one. Also, it is not good for use cases where the user needs an immediate response, like language translation. Online prediction is better for that use case. What are the pros and cons of online prediction? As I just mentioned, online prediction is tailor-made for use cases that require real-time responsiveness. Similarly, it is easier to prototype using online prediction because you immediately get feedback and can iterate quickly to improve the model. However, the problem with online prediction is that it takes significant computing power and infrastructure to do it in real time at scale and at a low enough latency that is acceptable to users. Also, this added complexity in real-time transport infrastructure means that service disruptions or system failures are more likely to happen here than in batch prediction. So what happens in a system that combines both data pipes for batch and online streaming predictions? To leverage the strengths of both batch and online prediction, a unified pipeline can be established. This approach combines the efficiency of batch processing with the responsiveness of real-time data handling, creating a flexible and scalable solution for diverse machine learning deployments. Sounds easy enough, right? Yeah, it's too easy. So the previous slide was kind of like a dummy slide. It was an untouched AI-generated platitude, which completely ignores the challenge in implementing this hybrid system. The book emphasizes that this is difficult in practice because the two different pipelines can easily cause bugs in production. Many times, one change in the pipeline isn't correctly replicated in the other, resulting in the system extracting two different sets of features. Why? Because sometimes different teams work on each pipeline without close collaboration. So sometimes just having a streaming pipeline by itself isn't fast enough to generate predictions for the user. Now what? You can do three things to improve speed. One, make the make new hardware to run the model faster. 2, make the inference faster, aka inference optimization. And 3, make the model smaller, aka model compression. 4 ways of which will be covered in the following slides. The first method discussed in the book is low-rank optimization. This involves replacing high-dimensional tensors with lower-dimensional tensors to reduce the number of parameters, resulting in a reduced model size and faster inference. One type is compact convolutional filters using image recognition, like squeeze nets, replacing the 3x3 convolution with 1x1, achieving the AlexNet level accuracy with 50 times fewer parameters. The issue with this method is that it is specific to certain types of models, like for convolutional neural networks, and not widely applicable to many use cases. The second method is knowledge distillation. This is a model compression technique that uses a large, accurate teacher model to train a smaller student model. One example of a student model trained by a teacher model is this Dilbert, which reduces the size of the teacher BERT model by 40%, while retaining 97% of language understanding and 60% faster inference. So one interesting advantage of this method is that you can have 2 different architectures for the teacher and student. However, a big disadvantage is that it is highly dependent on the availability of the teacher model. The third method is pruning. The book makes a distinction between 2 types of pruning. The first, more common one, is weight-based pruning, which is set to set less important parameters to 0 while leaving the network architecture intact. This makes the network more sparse, which requires less storage than dense architectures. This is easier to do without hurting the accuracy of the model than the second type of pruning, node-based pruning. Node-based pruning is removing entire nodes of the neural network, changing the architecture and reducing the number of parameters. This is more compact, but it is harder to do without hurting accuracy. And a big disadvantage to pruning is that it can introduce biases into the model. The fourth and last method discussed in the book is quantization. This is the most general and commonly used model compression method, which generalizes across many architectures. Quantization reduces the precision of the neural net's weights, for example, converting them from floating point to integers. By using fewer bits to represent the parameters, you can reduce the memory footprint and improve computation speed by reducing the training time and inference latency. The disadvantage to quantization includes rounding errors, which can lead to big performance changes. Now, there are 2 motivations for model compression. The first, as discussed previously, was to make ML models run faster. The second is to make models small enough to be able to run in edge devices, whose performance is constrained by slower processors and smaller memory storage. Now, why do you want to run ML models in these smaller edge devices rather than the cloud? Do you like money? Or rather, do you like to save tons of money? So let's go over the pros and cons of ML in the cloud versus the edge. So you can choose to run ML models either on the cloud or edge devices. If you choose the cloud, these managed cloud services like by AWS, GCP, Azure, make it easy for you to get your model deployed and scale up and down according to demand. However, a big downside in the cloud is cost. For example, big organizations like Intuit and Pinterest spend hundreds of millions of dollars per year, and small to medium businesses spend in the range of tens of thousands to a few $1,000,000 per year. If you're not careful with your deployment settings, you can kill your startup by leaving instances running in the background, just like the story in Hacker News. So instead of the cloud, you can choose to run your model, or as much as you can, locally on edge devices. Doing this has several advantages. First and foremost, you can save money from little or no cloud compute. Second, you don't have to worry about network latency as much. And third, in terms of user privacy, you can avoid passing user info over the network. The problem with edge devices is that they're limited in power, both in terms of computational processing power and compute and battery power. So now Saket will go over new solutions for the problem of putting ML models, including transformers, on edge devices. Over to you, Saket.
So thank you, Vern. As Vern was mentioning, there are own set of problems for edge devices and cloud solutions. But I think over the few years, people have been looking at hybrid solutions and trying to actually understand what are the advantages and disadvantages and how can newer solutions account to them and things like that. So as he mentioned, I'll just like to reiterate a few points. That is, what are the problems with deploying ML models on the edge devices? So the main problem, as one already mentioned, is the limited power. Also, since these edge devices are tiny, there are good sets of problems associated to latency, right? Although they are real time, let's say your ML model is big enough and it needs some time to actually do the inference, there are latency issues. And again, there's always a compromise between performance and this latency. That is, you can decrease the size of your model, you can prune your model, but at the same time, there's also some loss in accuracy or loss in performance associated with them. So how do people generally solve this? As one mentioned, that there are a number of techniques, model compression and that is quantization and things like that. And also by design, people have tried to solve this in the past. Mobile nets is one famous architecture that most of us have already come across or probably read about it. And again, there are newer techniques like sparsity, distillation, and other sets of techniques like that. But what's interesting in today's ML era is hybrid cloud edge solutions. That is, can you find out a way to integrate both cloud and edge together in some hybrid fashion so that you can take best of both worlds and try to account for disadvantages of one by the other? So how do people usually do it? So let's say you have a ton of processes and information and ton of data coming through your edge device. You selectively push not so important data to the cloud so that there's a bigger ML model on the cloud which can run the inference and keep the predictions ready. And whenever your task or whenever your application needs it, the edge device can pull those predictions from the cloud and just serve it to the user. So again, there are lots of limitations and lots of advantages. If latency and immediateness is a requirement, this is probably not a very good solution, but gets the job done if you have good amount of data coming in. Let's say you have a data that is you have an edge device that is mounted to a vehicle, and let's say you want to train a machine learning model on this incoming data, but you don't necessarily have to serve the predictions as they come, right? So it's good to send the data that is coming through the edge device to the cloud, run a lot of algorithms, and then whenever you want, you can just deploy the modeler, uh, s- serve the predictions through the edge device back again. Also, there are other newer solutions such as collaborated federated learning. Uh, Again, the main idea of federated learning comes from the fact that let's say a user does not want to share their data, but but still wants their data to be a part of the training process of the machine learning model. So there's a big concern of privacy here. That is, you don't want the data to leave from your device, but how can you still do solutions by actually using cloud and then train models collaboratively? So this is again a notable framework and a notable method people use in current industry frameworks. Can I get the next slide? Thank you. So one important slide that I wanted to talk about was how do people usually, are focusing on deploying transformers on edge devices. This is a very important uh, slide, I would say, because transformers today have essentially become the backbone of ML. Everyone today wants to deploy transformers for their own kinds of applications. Let it be just conventional NLP tasks or even a lot of vision-based tasks, right? So, what's the problem with transformers? You all must already know that these transformers have these huge blocks of multi-head self-attention. So usually it's uh, 8 plus or 10 plus heads of multi-head self attentions in each transformer blocks. So all of these attention blocks have this calculation of dot product attention. That is, you have these key, query, and value sets, and you have to do dot products to see which keys associate good with a particular query vector, right? So these are too much computation, and I mean, essentially, these are lots of matrix multiplications and are an overkill for on-device memory and battery support, right? So you'll have to keep in mind, can the edge device perform these kinds of activities or not? So how do people solve it? Existing solutions, I mean, some of which are also exciting and not so exciting, are reducing the quadratic complexity to linear complexity. That is basically dot product attention. Can you try to linearize it? Can you bring down the complexity from O of n squared to O of n? And I mean, this can be done by lots of ways. And also, can you see whether you can lower the precision? That is, let's say you are using floating point 32 and now you want to switch to floating point 16, or let's say integers, and then use some kinds of approximations or use some kinds of scaling factors to do it quickly, but with some loss in the performance or some loss in the precision. Also, this is a very exciting solution I found. There was a new hardware solution. So this device called Swiftron, it is a hardware accelerator that has been specifically designed by keeping in mind the transformer architecture. For people who must have delved into CUDA and how generally a GPU is constructed, you know that there are lots of limitations from the hardware side itself, which needs to be taken into account when you're actually designing them for ML applications. So these are, I mean, different techniques, such as how do you place your CUDA cores, and let's say you have multi-core, multi-thread GPUs. How do you place them such that there's less data movement and higher latency and things like that? And also, this paper also talks about how do you convert the calculations to integer 32 and then use scaling factors for correction, which I just mentioned in the above solution. So these solutions are something very new, and yeah, I hope to discuss about them if anyone's interested. Back to you, One.
All right, thanks, Saket. Although Saket did cover some topics relating to the challenges and solutions to running ML models on edge devices, the book goes over additional topics seen below, which covers a bit of the inference optimization and the hardware backends being developed to run ML models faster. So for the sake of time, we won't cover them in this presentation. But for the YouTube audience, if you don't have the book yet, please click on the link to Chip's website for multiple ways to purchase her book. Her website also contains our free online book on machine learning job interviews. So feel free to check that out. And finally, if you want to learn more about Gamma, the Gen AI tool that I use to generate 75% of this slide deck, click on the link to this Tom's List, a newsletter by this former Google product director who compares the various Gen AI presentation solutions in the market today. And I'll drop a link in the Discord for a Gamma referral link where you can get additional 200 credits for signing up for a free trial. And with that, I'll end the YouTube stream. And for the book club members on Zoom, please stay on for discussion topics and breakout rooms. Thank you.